Test, test. All right, hopefully let's check it out. Oh, I don't like, this doesn't seem quite properly set up at the moment. Let's just take a second to change some of these properties real quick while we still can. Can we pan this down a little bit further? Oop, no, tilt. Is that what we want? Yeah, we want tilt. Seems a little bit better, right? Hi. Is that good? It's hard to tell with these things. Hopefully that works. Ugh, get this hair out of my mouth. All right. Hello, everyone. Let's pop this out just in case. Always with the just in cases. Yeah, everything looks good. Looks like we're streaming. Looks like we're recording. Looks like we got good bit rate. Yeah, hi, puppers. My apologies for missing my stream yesterday. Bit of a busy day. Things just kind of pop up every now and then. I did get some studying done, not as much as we wanted to, but that's okay. Today I did get a resource in. So my last stream, not yesterday, the day before, I talked about new resources, specifically the CCNA official guide, the hard copy book. So here we go. I got the library version, which actually gives you both Volume 1 and Volume 2, as well as access to all the different labs and stuff like that. So pretty neat. I got it from the most popular of internet book retailers. I have a membership there, so it makes things a little bit cheaper. I also, being someone that bought it that way, I probably shouldn't say this, but I do support local sellers. So if you're gonna get it, probably try there first. I should have done that, but the ease of internet access, right? Oof. Anyways, so I got the books. Super pumped about it. I'm going to finish Neil Anderson's video series course first, and then I'm going to follow up with the books instead of Bombell's video course, just because I want to add some reading. So I'm super pumped about this. It's going to help me fall asleep at night. It's also just going to give me that extra little bit. And based on what I've already read within the first volume, I covered like the intro stuff in it. I'm super excited. It seems to be really well laid out. It seems to cover information in a better, I don't want to say necessarily the order's better, but just how it packages the different chapters together to create kind of like subparts. And then it has quizzes at the beginning of every chapter, and then you can create larger quizzes out of those base parts if you add a bunch of chapters together. Basically, I'm saying it's just a really good resource for learning the exam. So I totally understand why this is the one that Cisco puts its stamp on, as it seems to be really, really well thought out. So again, I'm excited about that. But with that out of the way, today I'm hoping to cover network redundancy, more specifically the protocols that we use in layer 3 and layer 2 to allow us to have redundant networks. So before this, when I talked about network redundancy, I talked about it specifically just in devices. So having more than one router on a level so when we talked about like spine leaf distribution, to where you have the spine and the leaf allows the access, so you have end users going into the leaf, and then the leaf goes up to the spine. So you have essentially two network tiers, and it allows for faster throughput because you're not tying up all the bandwidth on the way up to the spine. Like you know how it works. I know how it works, kind of. I'm getting better at it. But even with those physical devices, without what I was getting at, without protocols to enable the redundancy like safe secondaries and official primaries within those systems, you're still going to have a lot of unnecessary traffic, even with in fact, even more so with the redundancies, because you have access layers being or end users going up to access layers. Maybe even if they're a server, they have two connections to an access layer, and then they're spamming out even more broadcast packets than are necessary. It floods your network and it brings it all down. So it's not just about adding devices. You also have to have protocols within those devices that allow that redundancy to work without just adding unnecessary broadcasts, unnecessary packeted information to your links, to your bandwidth. I'm not entirely sure the verbiage I'm looking for, but that's not quite it. So we're going to start on layer 3. Layer 3, as we have learned, is the layer in which routers are placed. So we're going to be talking about protocols that affect routers, which means they're going to be working on IP. They're going to be working on that layer. So if it was layer 2, we'd be working with MAC addresses, but it's layer 3, so we're working with routers and IP versus switches and MACs. So with that in mind, layer 3 redundancy protocols are known as first hop redundancy protocols. There's actually, I think there's 3 of them total. I believe I had this in my notes. But I'm not actually seeing the 3. Advanced details. Nope, that's all for hot standby router protocol. Okay, so I know there's other options, but all of my notes are for the for a specific one, and I think that's because, if I remember correctly, this was notes from yesterday, not today. If I remember correctly, the one I took notes on is the only one that the Cisco exam deals with, and it seems to be the standard used across the industry. That being said, it's important to know that there are other possibilities, just in case you run into them at work. So we aren't just studying for the exam, we're also studying for work, so we're going to keep in mind that there are some other ones. That being said, the one we are interested in is the Hsrp, the Hot Standby Router Protocol. This is a protocol that follows under the first hop redundancy protocol. So when we're talking about redundant protocols for layer 3, they're known as first hop redundancy protocols. There are 3 of them that I remember. I remember specifically that there were 3. I don't remember the names of all 3. The one that we're going to specifically go under is the hot standby router protocol. So this protocol uses a virtual IP known as a VIP. It also uses a virtual MAC address, and there is no nifty little like virtual IP is VIP. There is no like VMAC. It's just MAC address, virtual MAC address. And so this is gonna, why do we have a virtual IP and a virtual MAC address? Well, what we're gonna do is between the primary and the standby router, so the active and the failover, or what is it, active passive or active standby? I think it's active standby. So between the active and the standby router, there's going to be this virtual IP and this virtual MAC address. So when we're pointing hosts from the access layer or even from the user layer up, we're going to be pointing them towards that virtual address. We're not going to be pointing them specifically towards the interface on router 1 or router 2. We're pointing them towards this virtually made up address in between them. That way, if either router 1 or router 2 goes down, you're not losing that IP address that's associated with the physical interface, because you're using this logical virtual one. So even if the interface fails over, you're going to be using that same address. It's just going to route differently to get there. So that's a real neat, that's kind of the basis of how this all works. So super neat. So the host or the active router uses the virtual IP address as their default gateway. So again, so this is just so it's not using its physical interface address. So there is going to be a physical address that is going to be a direct access on that router that they're all going through, but it's not pointing to the address on that physical address. It's pointing to the virtual made-up address that's put between the two routers. So this is just a way to prevent if that interface goes out, it doesn't have like this whole like, wait, where am I going now? It still has that virtual address it's pointed towards. It's just going to take a different route to get there. It's going to go through the standby router versus the active router. So the standby will become the active if the active goes down in that case. This provides gateway failover. So this is our redundancy, right? One router goes down, the other router's still up. It still has access to that virtual IP, that virtual MAC address. So the network continues to run. Like there's going to be a little hiccup while everything sends out their hello packets and goes, hey, this interface is down, this interface is still up. The virtual IP is still there, so that's still there. We just have to take this alternative path to get there. And this would be easier with some labs. Unfortunately, I still don't feel comfortable creating my own labs, and I don't want to use the labs that are accessible to me through the through Udemy. So apologies, but again, this is we got some time. We got quite a bit of time yet before the test date, so hopefully that week, maybe even before then, I'll be able to actually lay this all out as I'm talking about it, which will add a whole different layer, a visual layer that you can follow along with. So advanced detail of hot standby router protocol. And hey, we know it's, so maybe it's not active. Maybe, well, yeah, no. Detail. We know it's active standby because it's called hot standby router protocol. It calls it standby, so we know that's the name of the device that's not currently active. So the interfaces that are running Hsrp, there's going to be that virtual interface between the two routers, and then there's going to be the actual interfaces that are going into the information. Those are still going to have, like I said above, and I apologize, I keep bumping my mic stand. I don't know what that does, but I imagine it's not great. Interfaces, they're still going to be running their normal physical IP address and MAC address. I covered this above, but just kind of like to continue covering it. They still have a normal physical IP address. They still have a normal MAC address. It's just you're not pointing towards that. You're pointing towards that VIP between them and the virtual MAC address, depending if you're working on layer 3 or layer 2 data. Man. Yeah, so when online, one is elected the active router and the other is the standby, and that actually does matter when you're mapping out your network, because you're going to want your active router to align with the other redundancies you have on layer 2, and we'll go over that a little bit later. But there is a reason why you would want to preference one active and one standby versus just letting the systems choose it on themselves, which they do have default means of doing that. So This is all silly. I've already talked about all this. I'm not going to continue to repeat myself. How does failover happen? Okay, yeah, this is good. So failover. Failover is when the active router is no longer able to send or receive commands for whatever reason. So the router sends hello messages to each other over their shared Hsrp interface. If at any point the standby stops receiving hellos, it will transition into the active router and take ownership of the VIP and virtual MAC address and respond to ARP requests. So the shared link between the two, the active and the standby router, the one that they paste their virtual IP and virtual MAC address over. I have to look closer into this because this makes it sound like there's an actual active link in between the two. But if I remember the interface right, I don't. And this is partly because Neil doesn't have he doesn't have keys for his networks. So sometimes things mean one thing and sometimes they mean something else. So I have to look into that. I'm going to make a note for myself. Look into if it's a physical cable or just a virtual connection directly between active and standby routers. This should be pretty easy to figure out. It's just something I'm blanking on. But it is super important, right? You need to know if that's an actual, is that going to be a physical interface that we connect between these routers, or is it just a virtual one that it creates itself and then routes the data around to pretend that it's there? I have the commands here. This is all fairly... Man, this just doesn't really make sense without actually going through a lab. And again, I don't want to bring up labs that I don't own and share them. Even if no one watches these videos, it seems like that's a shady thing to do on my part. So I'm going to not do that. Check it out. I found in the very bottom of my notes where I labeled the three first hop protocols that he talks about. So I did. So there's the hot standby router protocol, which is the one we've already talked about, the one we've been talking about this whole time. It's a Cisco proprietary deployed in active standby pairs. Then there's the virtual router redundancy. Redundancy. I can spell. Protocol, also known as the VRRP. This is an open standard. Well, that's interesting. Usually it's open source. I wonder if it's open source but the standard. Deployed in active standby pairs. Again, so that's the same. Very similar to Hsrp. I'm guessing the difference is this is Cisco proprietary and this is an open. I'm guessing this is open source and possibly the standard across the industry because it's open source, which, I mean, I don't know, Cisco. Seems like you, I don't know if you're winning out on these, but I mean, I guess they've done the math and they take in more than they lose with their keeping their stuff to themselves for the most part. Load balancing across multiple routers. Awesome. Okay, so here's the three choices. We got hot standby router protocol. That's the Cisco specific one. Is deployed in active and standby pairs. You have the virtual router redundancy protocol. So this is essentially the same thing as the hot standby router protocol, only it's an open source and possibly the standard. So let's maybe the standard. And I keep bumping this thing. Again, deployed in active standby pairs. And then the third choice is gateway load balancing protocol. This is again Cisco. Cisco controls this. It's their IP, their intellectual property. However, this one supports active load balancing across multiple routers. So that's pretty rad. That's awesome. That helps with bandwidth allocation and things like that to keep your network running nice and smoothly, no matter how much data's clogging it up. Or to help it run that way anyways. It doesn't necessarily guarantee it. So cool. These are the three. However, based on what Neil said in his notes yesterday, I know for sure he said that this is the one that's most likely going to be tested over the hot standby router protocol. So that's the one I'm going to spend the most time studying, but it is important to remember that there are some other choices, specifically that this one is open source and essentially the same thing as Hsrp. That makes it really easy to remember. And then the gateway load balancing protocol, as long as it's said that way and not as an acronym, it's really easy to see the difference. It's got load balancing in it, so it's going to allow active. However, if you just see the acronym, you need to know what it stands for, because knowing that name, knowing that it's load balancing, that gives you everything. That gives you everything you probably need to know for the question, because it's going to be a question that comes down to the differences between these protocols, right? So it's going to give you a question in which you're going to want to have a load balancing active setup, or it's going to give you one in which you have to use an open source protocol, right? So if these two are Cisco, this is your only choice. Or it's going to give you one where you have to use a Cisco, but it wants to have a standby. It doesn't want to have them both active, and there'd probably be reasons for that, right? So, I mean, it's important to remember these in the way that you're likely to see them on the test. I mean, or to study them in the way that you're likely to see them on the test. That being said, it sounds like these two are more than likely not even going to show up, right? So you need to know that there's more than one protocol possibility for first hop redundancy protocols on the layer 3. That being said, you're more than likely going to be tested on the hot standby router protocol. So, study accordingly, right? Like, we want to know as much as we can for when it comes to the job, but we also need to know specific things for the exam. So keep it in perspective, right? That being said, the rest of my notes for yesterday seem to be a lot of commands. And again, I do like typing these out for myself, just to build that muscle memory, to build those pathways, but I just don't know how much it really transfers, because there's no response. It's not an actual CLI that I'm typing into, and I can't give you all the information that pops up on these like show routing protocols and stuff, because I just don't know it all. So here's a couple of advanced features for Hsrp. That's hot standby router protocol. Here's a couple other features. Let's just go through these real quick. You can choose which router will be active by setting its priority. Higher priority will be preferred. So this is interesting, because this is one of the first times that a higher number is preferred. Usually it's the lower number, right? Almost everything we've learned up until this point, it's lowest number wins. But this time it's like, hey man, highest wins, and it's going to default. So if you don't choose to change it, it defaults to 100. So that means every router that you set Hsrp up on, it's going to default to 100 unless you change it. That being said, so if you don't change it, if all the routers are tied, or in this case, since you're going to be pairing, if the two routers are tied, the highest IP wins. And again, it's the highest. Very interesting. And you know what? Now, so it has to be a physical link between these two. I was remembering it wrong. So it's a physical link that broadcasts the virtual identity by the active router. That makes sense. That makes sense. So there is going to be an actual IP associated on both sides of the interface. And the highest IP is going, if the priority is tied, then the highest IP is going to choose which router is active. At that point, that active router is going to change its gateway to the virtual IP, right? So it's still going to have that physical IP address associated with the interface, but the gateway is going to change as it becomes active to the virtual IP address. And that way, switches, router, no, it wouldn't be well, would it be routers? I suppose so. Router, anything on the network below it will know to point towards the virtual interface, the virtual IP, the virtual MAC address, versus pointing at specific interface IPs. Renable higher priority. Okay, so here's another. Here's another command you can have. You can either have it preemption on or off. So preemption will re-enable the higher priority router once it comes back online after a failure. So if there's a failure, if the active router goes off, the standby router becomes the active. If you also included the preemption command when you set up Hsrp, when the active router comes back up online, either by itself or you manually reboot it or whatever, it will once again become active. That being said, if you did not include, which I believe is the default. Yep, this is the default. So it does not default to the on position. That means the lower priority router will remain the active even after the failed router is brought back online. So there's reasons for either one of these, right? So there's a case to be made that you would want the previously active router to become the active router again, right? So that's probably how your network was designed to be. So if it was just this router that went out, all your systems below stayed the same, then you probably do want this to become your primary router again, because that's how the rest of your network is set up, to be pointing towards that as the primary. That being said, if you set it up so that it becomes primary as soon as it boots back up, there could be a situation where this router has an issue to where it's constantly restarting. So every time it restarts, it becomes the primary, then it shuts down, it becomes the standby, and the other one picks up, and then it comes back on, it becomes a primary. And you can see how that would really screw the network up, because the network would be constantly the two routers for one would be sending hello packets to each other, and 1 second it would be on, the next second it would be off, 1 second it would be on, the next second, or whatever the interval would be. You could see how that would cause a lot of issues from there down, as all the other systems, they wouldn't have to change their the IP they were going towards, because they'd be at that virtual IP that was between the two, but the route would still change as those interfaces were going up and down. Yeah, neat. So there's a reason why you'd want it on, there's a reason why you'd want it off. But it defaults to off, so it means you would have the network administrator would have to go in and re-enable the previously primary router as the primary again. And that might just take because it already is the lower priority. I wonder if there's a specific command you would use to enable it without including preemption and the next time it went down. I wonder if there's that's an interesting question. I wouldn't have thought of it if I wasn't explaining it on here. So that's something to look into tomorrow. And then again, the rest of this is just a lot of commands I wrote down on how to enable this on different addresses. Stuff like that, but it doesn't seem like that's going to be very helpful in the moment. So let's move on to layer 2. So this is all layer 3, right? That works on routers just fine. But of course, below the routers, if we're thinking of this as like a tier system, is layer 2 with our switches. And layer 2 switches also have redundancy, right? You're going to have a lot of access servers switched into other access servers, switched into the tier higher than them. Depending on what system you're using, it's going to be like your core, or maybe it's there was like a middle system you could be. That was notes from a couple days ago. Got to keep studying. The point being, even just by connecting them to each other, like sharing a couple of different connections between switches, again, without that protocol, you're actually hampering your network, because switches, unlike routers, they broadcast like crazy, right? They can't rely on IPs to find things. They rely on MAC addresses, and until they know that MAC address, they're just sending out broadcasts like, hey, find me, on FFF. Find me this this IP address. I have no idea where to go for it. I don't know the MAC address I'm supposed to go to. Therefore, I'm just going to spit it out everywhere. And then every router continues to spit that out everywhere. And that can actually create loops, which is what we're going to talk about today. So layer 2, you enable spanning tree protocol. So spanning tree protocol is actually like, again, layer 2 specific, because the hope is that it doesn't get this far, right? The hope is that the layer 3 figures out that something's wrong before it gets to this point. It's like, hey, the way you created this, not so good. But the great thing about spanning tree protocol that we're going to get into is that it's kind of like, it's enabled by default. It is defaulted on all these routers, so you just set them up, and it's going to figure it out. It's going to say yes, no, yes, no. So you don't really have to do anything, but knowing how to manipulate it can make your network so much better, because again, we want the protocol at layer 2, we want those primaries and standbys to match up as best we can with a protocol from layer 3. That way you have as few hops as possible to get information up and down the tree, right? So if we think of the whole thing as like a tree trunk, and then the branches out and the roots down, all the users are kind of like these roots, the very ends of the roots, and they're coming into the access layer that kind of starts to become the trunk, and then you move up to that middle layer that really is kind of the trunk, and then I don't know where I was really going with that, but spanning tree protocol is incredibly important to networking. It's important to your career. It's important to the certificate exam. It's going to be a big topic, much like subnetting is. Like, it's one of those things that you need to understand. So spanning tree protocol, STP, is layer 2. It is enabled on switches by default. It is a technology, actually I should say a protocol, that prevents loops from bringing down your network. So what happens with a loop is that you have this broadcast that's going around and around and around, and there may be, even if you're really unlucky, there's just going to be more and more broadcasts because the information can't be found. So the system just continues to be like, hey, where's this? Hey, where's this? And it just keeps going, and then it builds and builds, and there's more and more of it in the line, and then it literally takes over all your bandwidth, or overloads your buffers, and it brings down the system. So it's super important to be able to prevent these loops from happening. And of course, we physically connect these devices so that loops will and can happen, right? Physically, they're connected to the point where you have these circular paths between all these different switches, and those are the redundancies. But we don't want all these paths active, right? We don't want them all actively broadcasting out, forwarding information. That's where the loops happen. So what we need to do is we need to find a way in which the information can be broadcast out, but it's not creating feedback loops. So it's broadcast out, but it eventually gets to where it needs to be in the shortest amount of hops as possible without creating loops. And so it has to map out the network, and we'll talk about how spanning tree protocol does that. So it is an industry standard protocol, enabled by default on all vendors' switches. So it doesn't matter if it's a Cisco switch or what, this is gonna be there and it's gonna be enabled. And so what does it do? It uses the bridge protocol data units. This is the first thing it does. So as soon as you turn on a switch, first thing it's gonna send out its interface is a bridge protocol data unit. Sent out all ports when a switch is powered online. These bridge protocol data units, let's call them BPDUs. Man, that sounds so military. Detect other switches and potential loops. So as soon as you power on the switch, all the active ports are going to send out a bridge protocol data unit, a BPDU, and the intent of that BDPU is to find any other switch on the other end of that that interface connection. And when it does, it's mapping it out, and the point of that map is to eventually prevent loops. Important to note it that no traffic will be forwarded out of the port until the switch is certain it's loop free. So again, STP is on by default. This is what's going to happen by default until until STP is satisfied. Specifically, this would be the BPDU portion of it. Switch comes online. All ports are first in a blocked state. And that's not, so when I say blocked state, I'm not saying all traffic. This is for broadcast traffic, right? So STP has no interest in blocking like unicast, I don't believe. Like, I think it's just broadcast traffic that it prefers to switch onto these lines. I gotta look this up, but I feel like it really is, like, right? Maybe not. Maybe it's all traffic. No, it's got to be just broadcast. Because that's the only thing that I don't see how. Shoot, maybe it's all traffic. I gotta know this stuff better. Working on it. All right. BPDU detect if the port will form a potential loop. If no loop is detected on the port will transition to a forwarding state. So yeah, that makes me feel like forwarding means it allows broadcast. I feel like that's not specific to unicast though. So the big drawback of spanning tree protocol is that this process can take up to 50 seconds. And 50 seconds may not sound like a long time to us, but in computer time, when they're doing all these microtransactions, it would boggle our mind. 50 seconds is an eternity. Especially when your network traffic is on the line. 50 seconds is like, let's get to it. And this is because it's doing a lot of mapping. And it's also an old protocol, so we'll figure out how we can fix that a little bit later. Real quick, we've been talking about bridge protocol data units, the BPDUs. What does a bridge Sorry, trying to type and talk at the same time can be confusing. What does a bridge protocol data unit contain? Where was I? Lost myself in the notes. So what does it contain? Question mark. It contains the switch bridge ID, which is a unique ID for the local area network. So the switch that it's on is going to have a unique bridge ID. We talked about this before in other protocols. So other protocols, you could assign like a loopback to be your router ID. But for this one, it's going to be the bridge ID. So again, this is going to be a unique ID. So what is this unique ID made out of? Whew, man, I'm talking in circles. The bridge ID is made up of the switch's unique MAC address. So again, every device that is created has its own unique MAC address. I forget exactly how long they are, but the first couple of numbers on it is specific to the vendor. So like ASUS has their own, LinkState has their own, and then the second set is a unique identifier, and it just goes up by one every time they create one, I suppose. And then each company has their own, like, just like ISPs, they have their own like unique chunks associated with each of them, so they don't accidentally. Well, I guess the first part would make that unique, right? Even if they had the second part the same, the first part would be different because one was ASUS, one was LinkState. Man, creating knowledge by just talking myself. I hope I didn't confuse anyone with that babble. So the bridge ID is made up of the switch's unique MAC address and an admin define bridge priority value. Doesn't sound right. Admin defined. I think it's admin defined bridge priority. Oh yeah, so what I mean by this is a network administrator, network admin. So part of the bridge ID is going to be made up of the unique MAC address that's associated with the switch. Every switch comes with one. That's nothing that you can do anything about. The other part of the bridge ID can be set by the network admin defining priority value for that bridge. Of course, there's a default one, so there's always going to be that. But if you wanted to change the default, that would also have an effect on the bridge ID. Boom, boom, boom. All right. Bridge ID. So the bridge priority value can be anywhere from 0 to 65535, 65,535, with a default of 32,768. So our bridge priority, the part that we can define, the network administration can define the bridge priority. So that's a command that you'd put in the CLI. It can be anywhere from 0 to 65,535. The lowest value is preferred. So yeah, the lower this value, the more likely that bridge would be chosen as the primary bridge within the spanning tree protocol, which means a lot. It would choose it as the root bridge. I don't think we've gone over that yet. No, we haven't, but that's what it would do. And the root bridge is rather important. So this is a way that you can manipulate the commands to choose which switch on your network is the root switch. Boom. I'm sorry, root bridge. They call it a bridge. It is a switch. This is just terminology. We can go into why, but it's not necessary. It's really not necessary. So just learn the terminology. Switch and bridge are the same thing. Same devices. In this context, I don't believe there's any other context. But for this instance, when you're using STP, the switch with the lowest bridge ID is going to become the root bridge. So what does it mean to beat the root bridge? Well, it means the switches using STP build a loop-free forwarding path tree that leads back to the root bridge. So the root bridge is your primary. It kind of builds out and back to it from there. And at no point do you want a loop to form. So it's the best. It creates best paths to the root bridge, or from the root bridge, I guess is where it would create them. It'd create them from the root bridge. So that means you would want it on one of your upper layers, probably pretty close to your router, if not bumping up against your router stage or your router tier. That way, everything is built up, so it's giving you the least amount of hops up to your next tier, from layer 2 to layer 3. That's how it would make sense to me. But maybe there'd be reasons to have your root bridge near the bottom. I don't know. So again, the root bridge is elected off the bridge ID values. So within that section of the network, the lowest bridge ID is going to become the root bridge. In case of tie, lowest MAC address decides. Well, of course it does, because it's made up of the unique MAC address and the defined bridge priority value. So if you don't change anything, if you just plug in all your switches and you don't change any priorities, it's going to be your oldest switch is going to be your root, because technically the older a switch is, the lower the MAC address value is likely to be, because it's an older value. It's an older model, which means it was made earlier, which means it was earlier in the up, unless they're going down, but I'm assuming they're going up from 0 to how many ever. Which is interesting. So if you default it, that means you could be putting your worst switches as your primary. So that's something to keep in mind, right? Probably don't want to do that. So what are some other terminology? We know root bridge. There's also root ports. So if we think of root bridge as the device, root ports are going to be interfaces within a device. So the interface with the lowest cost path to the root bridge is the root port. So if we think of a switch as being the root switch, and then there's another, if we think of like a star pattern off of it, all the switches that have direct connections to that root switch, that's going to be their root port, right? Because that has the lowest cost path back. And that's really easy to figure out. It starts to get harder as the switches get further and further removed, but still it's going to be the lowest cost. So whatever the lowest cost path back to the root bridge is going to be your root port. The higher the bandwidth of the length, the lower the cost, which makes sense. So the faster that line goes, the lower the cost. Again, if you're someone who plays a lot of internet games, we can think of this in ping, or what is actually latency. So how quickly your information gets between you and the server. The faster that path, the faster that connection, the lower the number, the better, right? So a ping of 10 is much better than a ping of 200, and that's because you have more bandwidth. You can get there faster. Yeah, so the faster you can get back to the root bridge, the better, and that's going to become your root port. If multiple paths are found back to the root bridge with the same cost, which can happen, the switch will choose the neighbor with the lowest bridge ID as the root port. So if you have multiple choices back to the root bridge and the cost is the same across all of them, then it's going to choose the path based on the next jump. So it could be multiple jumps, but it's going to base this choice on the next jump whichever one of those switches has the lowest bridge ID, which again is made up of their switch MAC address and the priority it was set to, is going to be chosen as their root port. So that could be a little bit confusing, but stick to it. It gets easier and easier on that one. I didn't actually write that out, but we'll pretend I did. So what does this mean? This means there is no load balancing, right? So even if there's multiple paths back to the root bridge, it's not gonna send some data on one path and some data on another path, which would be load balancing, right? Because you're not forcing all that information off on one connection, which would could overload it, right? So you're not balancing the load, you're overloading one stream. But because we have this priority and we only have one root port, if all the costs are the same, that means you can't load balance. So that's something to think to keep in mind too. Like, we're preventing loops, but we're also forcing data on very stringent paths, which could cause, like, you know, bandwidth allocation problems on those single lines that are chosen as the primary. Not even the primary, the active, essentially. Reports. Another kind of port we have is a designated port. Designated ports. So these are the ports on the opposite side of a root port. I guess I should be capitalizing that. So our root bridge is broadcasting out. What's pointed back towards us on the fastest. So if we are the root bridge, we're broadcasting out. All the interfaces facing towards us, the quickest ones back to us from each device are going to be known as root ports. So their root ports are facing back towards us as the root bridge. The designated ports are on the opposite side of a root port. So every root port is going to be an interface, and it's going to be directly connected to an interface on the other side. That's going to be a designated port. It really sounds all kinds of confusing, but it really makes sense, especially if I was able to pull up a decent packet tracer. It'd be a little bit easier to understand, but so designated ports are on the opposite side of a root port. If you have a root port, on the other side, there's going to be a designated port. So that means all ports on a root bridge are designated ports, right? So if the fastest path back to us is a root port, and every direct connection to a root bridge would be the fastest path, that means they're all going to be root ports. That means the interfaces on the root bridge are all going to be designated ports. Whew, man. I mean, it sounds complicated, especially the way I'm explaining it, but when you look at a picture, a network map, you're like, oh, yeah, no, that makes sense. So that means designated ports will always be facing away from the root bridge. Again, not easy to think of without a map, but with a network map, it's like, oh yeah, they are always pointed away. And that means root ports will always face toward the root bridge. So again, this is going to make it really easy when you're actually creating the maps to be like, oh, this would clearly be a designated port. There's no way it could be a root port, or vice versa based on where it is in association to the root bridge. Man, I know. It's a lot of me just saying root over and over again with another word after it. And if you don't really understand it, it's just words, man. So again, I'm just kind of restating things over and over again to a simpler and simpler form to get the point across. So that means root ports and destination ports are always going to make up the most direct paths to and from the root bridge, they will always be in a forwarding state, right? So again, because these are going to have the lowest cost, they're going to be the preferred ones. They're always going to be on. They're going to make up the direct paths because they have the lowest cost. So that's the same thing. Lowest cost means the most direct path, quickest path, highest bandwidth allocation. And because of that, they're always going to be on the forwarding state because that's where you want the forwarding information to be passed out. You want it to get there as fast as possible without creating a loop. All right, okay, so what does that mean for the remaining links? All remaining links then have to determine which of them has the least cost path to the root bridge. Again, the bridge ID is used as a tiebreaker. The lowest of the pairs are enabled as designated ports. So this is designated ports again, but we're putting them in a little bit different position. And that means so there's going to be pairs of connections left. Out of those pairs of connections, one out of the two is going to be closer to the root bridge, which means it's fewer hops. That's going to be the designated port, right? The opposite end of that designated port is going to be a blocking port. So blocking ports are the remainder of the above pair. And it blocks. It's still a physical connection. It still could be opened if, because again, this is all for redundancy. So if a switch goes down or an interface goes down, it's going to rework which ones are your root ports, which ones are your designated ports, and which one are your blocked. But in the current state of the network, these are going to be blocked ports. They're not going to transfer information, and this is to prevent that that loop from happening. So this is all to prevent loops from occurring in our network, and it works. You plug in switches, and this works. To the extent of how well it works is based on how well you set it up in your network. But this works. Just plugging in a bunch of switches, man, keeps them from bogging down the network. It's pretty amazing. So at this point, all ports should be either a root port, a designated port, or a blocking port, right? I guess I should capitalize all these because they are like an actual thing. Like you'll go into the interface and it'll be like, this is a root port. So they are what they are, man. So we can go through like the steps STP takes. So it's going to determine the root bridge. All ports on the root bridge are designated ports. It's going to determine the root ports on the other switches based on which ports pointing back towards the root bridge have the lowest cost. Ports opposing root ports are designated ports. Of the links left, one of each pair will be blocked. I guess it's blocking ports. Determine the highest cost path or highest bridge ID if all paths are the same. That's what it means by or highest ID. In case of tie, let's just say in case of tie. The highest cost is the blocking port. That means, whoops, well, whatever, 7. The ports on the other side of the blocking port are designated ports. So that was just me saying ports a lot over and over again. I understood it, kinda, just because of all the stuff I went through today, but man, I don't know. If I was just coming in on this conversation, I'd be like, does this person have like a issue? Like they just repeat stuff over and over again, or is this talking in tongues? What's going on here? So there's actually different versions of the spanning tree. There's 3 IEEE versions, which are open standards. IEEE, we've used that in a couple of other things. I can't off the top of my head remember exactly what it means, but it's like a board decision saying, yeah, this is a good standard. We like this. So number 1 is the 8021D. The D in this one is capitalized. And that is the spanning tree protocol. That's what we've been talking about this entire time. It's the OG. It uses one spanning tree for all VLANs in the LAN. So again, we're talking about switches. So that means when we're talking about the areas that they cover, that's going to be the local area network. So within this local area network, the 802.1D spanning tree protocol will use one spanning tree for all the VLANs within that local area network. The next option is the 802.1W. For some reason, the W is not capitalized. I don't know. This is known as the rapid spanning tree protocol. So you'll remember one of the things that we talked about being like a real big drag about the spanning tree protocol is it can take up to 50 seconds for it to go through all these, like, oh, what do I want to do? What do I want to do here? So this was an upgrade to that significantly improved convergence time. Still uses only one spanning tree for all the VLANs in the LAN, in the local area network. However, it improved the convergence time. And I don't remember, he didn't actually go over this yet. He may go over it in further chapters, but essentially what I remember from my networking days is instead of having the central root bridge send out all this information kind of out like if you imagine like ripples in a lake going out from when you throw in a stone, instead it has it like passed on from switch to switch, but it just does like just between those two instead of like a wave. It's like these little microtransactions, and it speeds it up. I have to go over that again, but it really improved convergence time. And he didn't say specifically how fast it was now, but he said in a matter of a few seconds, typically. So if we think that the original spanning tree protocol took 50 seconds, up to 50 seconds, a matter of a few seconds on this rapid spanning tree protocol, and it does everything else the same, that's well worth the upgrade, right? So the next one is the 802.1S, and again, the S is not capitalized for some reason on this one. This is also known as the MSTP, Multiple Spanning Tree Protocol. Much like the name implies, this allows you to enable grouping and mapping VLANs into different spanning tree instances for load balancing. So this is kind of a unique way to get your load balancing. Essentially what we're doing is we're taking this larger LAN and we're splitting it into smaller sub-LANs by creating VLANs that go through different trees. So we're creating multiple trees within one local area network, and then each tree is responsible for specific VLANs within that LAN. Woo! And that allows us to use specific routes for specific VLANs. So when we split those VLANs onto different routes, That's essentially load balancing, right? We're using different links. So we're not pushing all our information over one link, over one physical interface between these, just because it's the fastest hop. But when we split up the VLANs, we can have different fastest hops. And then we split up, so VLAN 1 goes on this side, VLAN 2 goes on this side, and they actually make their way up a different spanning tree protocol, and they may even make their way up to layer 3, at which point we can use an active versus a active passive layer 3, so we can use gateway load balancing protocol on layer 3, and then they can continue up their own specific trees. And we just built this really amazing network that has a bunch of load balancing built into it while also having redundancy. So we can see how these layer 2 and layer 3 protocols can work hand in hand with really building out a good network, like a strong network that has redundancy, but also allows for really good transfer of information up and down. So yeah, that's why you got to know this stuff. So there are a couple other spanning tree versions. So these 3 that we talked about just above, these are all open standard. So these are ones that you can get on indie vendors switch. The next ones we're going to talk about are Cisco versions. So these are specific to Cisco switches. You know, they do how they do. They like their specific software, and that's why we're here. So this one's known as Per VLAN Spanning Tree Plus, also known as PVST Plus. Super interesting name, right? Couldn't have made that much harder. Enhancement to 8021.d. So this is an enhancement. If we remember, 8021.d above was the OG STP. So it does everything. It's like an update to the STP, only it uses a separate spanning tree instance for every VLAN. This is the default on Cisco switches. So the interesting thing here is every single VLAN gets its own spanning tree instance. So up here, multiple spanning tree protocols enables grouping of VLANs. So when you're using multiple spanning tree protocol, you would say VLAN 1 through 15 takes this path, VLAN 16 through 30 takes this path, or some such, where you're grouping a bunch of VLANs together. Whereas the Cisco variant, the Per VLAN Spanning Tree Plus, every single VLAN gets its own spanning tree. So we can see how that could be pretty beneficial, right? Like if every single VLAN has its own path, that can allow for some really unique load balancing options, to where we're giving end users fairly unique paths, which means that they're not going to have a bunch of excess bandwidth being used on those links, because everyone's going to have essentially their own uplink to the, not their own uplink, but access switches are going to have more variety in their options. They're going to be using multiple links for different VLANs, and it's just going to help your network overall with bandwidth. Hey, bro. Hey, what's going on? Nice to see you here. So yeah, something to keep in mind. And again, this is a Cisco variant, so this is only going to work on Cisco switches, but it is how they're able to sell these devices, because, you know, if you want this stuff that works so much better, you got to have that Cisco equipment, baby. So they have another option. This is gonna be our second Cisco option, our 5th layer 2 spanning tree protocol version. So just depending on how you're looking at it, this one's known as the Rapid Per VLAN Spanning Tree Plus. So if we know what we know from the previous one, we're just adding Rapid onto the front. And we know that this one didn't do anything to help with the cycles when a network went down. So we can kind of guess that this inclusion of Rapid, much like the inclusion of Rapid to the 802.1W, just increase the convergence time. So let's see if that holds true for the Cisco variant. Yeah, looks like this is going to be an enhancement to the 802.1W, the rapid spanning tree protocol. So this significantly improves convergence time over PVST plus. So this, again, this is just like how rapid spanning tree protocol improved over the OG spanning tree protocol. But the difference being this is going to use a separate spanning tree instance for every VLAN. So again, once we figure out the open standards, the Cisco standard is essentially just adding one piece on top of each one, right? So that's pretty easy to figure out. If we know these three, these two almost explain themselves. I mean, except for kind of the weird wording of how they come up with the names, but that's its own thing. So again, the 802.1D spanning tree protocol, the OG, the original, is essentially just like the per VLAN spanning tree plus, only this one has one spanning tree for all VLANs. This one has one spanning tree for each VLAN. So a huge upgrade, but essentially the same thing. And just like that with the rapid versus the 802.1W. So again, this increased convergence time over the STP. This one increases convergence time over PVST plus, but same thing. Support grouping multiple VLANs. Okay, so something to note. Neither of the Cisco versions support grouping VLANs into the same spanning tree instance. So how this open standard, this 802.1S multiple spanning tree, how it enables grouping, there is no version of that for Cisco. For Cisco, each VLAN gets their own spanning tree. That's just how it works. One VLAN, one spanning tree. One VLAN, one spanning tree. So VLAN 1 will have its own spanning tree all the way up to VLAN 1 billion, which is not possible, but you know what I mean. They're each going to have their spanning tree. So this is important context for the exam. So if it's asking you which protocol would we use to group VLAN 1 through 10, then you only have one choice, right? If it's going to ask you which VLAN is best for load balancing, then it's going to be based on the scenario, because we know that you get load balancing by grouping VLANs, and you can also get load balancing by using the Cisco version, right? So it just depends on how precise you want it to be, because obviously Cisco's version is much more precise because each VLAN has its own spanning tree, and that's pretty rad. I mean, it's hard to beat that. I can't think of a setback to that versus being able to group them, but the only setback would be that these are Cisco proprietary. So again, it's that Cisco, you have to have the Cisco devices. That means you're paying Cisco device prices. That's the setback. You can't mix and match a bunch of different switches and just be like, hope it works. You'll have to go to an open standard in that case. And you'll probably have to do some network administration to the Cisco specific switches to downgrade them into the open standard, as they will want to run the Cisco protocols as their standard. So, you know, that's just job security, though. That's how I look at something like that. It's like, if you want this network to work, you better keep me around. So let's go over some, well, let's see here. It's been about an hour. It's been a little over an hour. So we talked about how we could manipulate the placement of the root bridge by changing the default value. So let's look at how we would actually do that in commands. So manipulating placement of the root bridge. And this is done by manipulating the bridge ID, which can be done by setting priority, right? So we can do this in our commands. We'll have to do this on each switch individually. So we would go into a switch, we'll say switch 1, we'll enable it to bring it up into privileged executive mode. Privileged. At that point, we'll configure terminal. No, configure terminal. Configure terminal. I couldn't spell there for a second. This will bring it into global configuration mode. At that point, we can enter our command. So it's going to be spanning tree VLAN. So you have to select a VLAN at this point. It doesn't have to be VLAN 1. I'm putting VLAN 1 as a holder. But you have to select a VLAN. And then you put root primary. So we're not actually giving it a number, even though it is associated with a number. Here, where were we up here? Here we go. Bridge priority value can be anywhere between 0 to 65,535 with a default of 32,768. So when we run this command, spanning tree VLAN 1 root primary, this is going to, this will set the switch router, switch priority to 24,576. And that will be calculated to change the root ID. But there's math into that, and that's not something we need to know. We just need to know what our priority is. So again, by setting it as the root primary is the key word within that command. By setting it as primary, that change the switch priority from a default value of 32,000 something to 24,576. So because it is a lower value, it is a lower number, it is the primary. It is the best choice. Boop, 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 boop. So we can verify this with a command. So we would do an end command to bring us back into switch privilege executive mode. At that point, we could run our show commands. So we're going to do a show spanning. Don't need to capitalize that. We're in CLI. Show spanning tree. Again, we're going to want to put the same VLAN. So I chose VLAN 1 above. And I didn't, in that situation, that'd be the VLAN running on the local area network. You know, you're not just choosing a number out of random. That has to be a VLAN that you've already set up and is running. But we're going to choose the same VLAN because we want to make sure we're verifying it, right? That's all we need to put in. We'll hit enter, and it will give us a lot of information, but one of the pieces of information in there will tell us whether or not it is set as the root bridge. But because all of what we've been talking about is network redundancy, so how do we set up a secondary root bridge, a failover root bridge, right? Use for the current commands. CLI is going to be your command program. I don't think I'm actually logged into Packet Tracer, or else I'd show you. Let me see if I can pull it up. Last time I don't think I logged in. Oh no, yep, no, it wants me to log in. I don't know my login off the top of my head. What is it? Let me see here. It's an email address. Is it this email address? I'm not broadcasting the screen, right? I want to make sure. I want to make sure I'm broadcasting the right screen. Okay, yeah, you can't see anything I'm doing right now. Nope, I don't know my credentials off the top of my head. But this is the CLI. This is the command line interface within Cisco. So when you are, this is what you're gonna get when you're either serialed in directly to the interface, or even if you call in over Telnet or SSH, you're gonna access the command line interface, the CLI. And it looks a lot like DOS. It looks just like DOS, and the same kind of command structure. So it's gonna come up, this is the name of the switch that we're on. We can change this if we wanted to. In fact, it probably wouldn't be switch, it wouldn't default to switch one, but we default at this level. We enable to get up to privileged executive mode. From privileged executive mode, we enter the configure terminal to get to the global configure portion of the system. So then we'd be configuring the global settings on this switch. Oops, this would be switch 1. And from there, we'd enter the spanning tree VLAN root primary. This is actually where we'd put in all our spanning tree commands at this level, I believe. There might be some interface specific ones, but I think most of them are going to be on the global configure. So yeah, that's all CLI. I wish I was logged into Packet Tracer so I could actually show you, but again, it looks just like it's very similar to your command line, just like DOS. So it's very similar to that. I haven't really gone over CLI, I don't think, but it's all very context sensitive. So for instance, the question mark will help you out a lot of times if you don't know the command. If you only knew spanning tree, you can put in spanning tree question mark, and it will give you your optional commands after that. If it doesn't have like set optional commands, it will give you like a context error, and then you know that you have to set in like something for yourself. So like VLAN 1 is something that we would create on our own. That might be like a context associated one. I don't know. I'm not that into it thus far, but yeah, I haven't really used it that much in depth yet either. Like I'm just using it to open. So if we look over here, here's all the chapters in Neil Anderson's stuff, and then the PDF that goes with the chapter, so you can follow along in notes. But then I also downloaded the lab for each one. So if I were to open this, for instance, this opens up Packet Tracer with pre-configured labs. So that's one of the reasons I haven't gone too in depth with Packet Tracer, because he's created all the labs for you, so you don't really have to create your own yet. But I mean, it's good practice too. I'm hoping to later on. And then there's also like a question and answer sheet. Okay, so that's the answer key. There's like a question that goes on with the lab, and then an answer key that goes with it, so you make sure that you do it right. But I'm not too in-depth in Packet Tracer, because all the Packet Tracer I've been doing so far has been pre-made labs, so, which is nice because you don't have to create your own network topology to practice on it, but it's also like it'd be beneficial too. So, you know, it's one of those things that I'm hoping to get more and more practice on. But as it stands, I'm just letting Neil build mine for me. So this is setting up your primary. Or actually, this is manipulating the placement of your root bridge. These would be the commands to set up your primary. So to set up your secondary, we can kind of guess what our commands would be. We're gonna pretend that we already got to the global configuration mode, so we're already in configure. And for the second one, it would be. So if our first one was spanning tree VLAN 1 root primary, this time it's going to be root secondary. That's right. Look out. And this command, will set the bridge priority to 28,672. which is, we can see, a little over 4,000 higher than the primary value, but it's still lower than the default value of 32. So it's going to be set as the secondary because it's higher than this one, but it's lower than the default. So it's going to kick on before the other ones kick on. That kind of makes sense, right? Again, we can verify it the same way. So we're going to verify by doing a switch 2. So if this would have been switch 1, this is going to be switch 2 because we're not going to put the secondary on the primary switch, right? And it's going to just be the same command, show spanning tree VLAN 1. So we do have to select the VLAN, but after that we'd hit enter. It'd bring up a bunch of information about all the spanning tree information for the VLAN, but one of that pieces of information would be the root ID, which would tell you whether it is root bridge, secondary root bridge, or just defaulted out. And you'd get that information off the MAC ID, right? Because this is all layer 2. So we would see that by the MAC ID. So I mean, I hesitate to go any further into that without packet tracer pulled up, because you need to show the packets to truly figure out what I'm talking about there. So we can kind of see, again, I talked about this before, but we can kind of see how these two different redundancies on both layer 3 and layer 2, how it's okay to let them default, but if you manipulate them to actively set your primaries in line with one another on the layer 2 and on the layer 3, it's really going to benefit your overall network. Because you're going to be creating a much more linear path, a much more logical path of information. Whereas if you allow it to default, you can end up with some really weird-looking layer 2 spanning trees, because you're going, again, if you default it, it's going to be your oldest switch that's going to be your root bridge, because it's based on the default and the MAC ID. So that could mean that one of your lowest tier switches, which could be located way in a weird locker on the first building that you were operating in with one of the lowest cost pieces of device, like it's really bad not to manipulate this with your network administrator, because if you allow it to default, it's still going to work, but it's not going to be as economical as it could be, right? You're going to be hurting your bandwidth. You're going to be slowing your network down more than it should be. There's some more advanced features with port fast, BPDU guard, and root guard. This is a way to kind of fiddle with the default spanning tree that gets set up without changing your bridge, your root bridge and your secondary bridge. Those will stay the same, but you can manipulate the path that is taken to get there by using these commands. However, they're not. You got to be careful, because using these commands can negate the entire effect of a spanning tree protocol, and you end up creating inadvertent loops on your network and actually further degrading your network, or possibly even bringing it down. So good commands to know. I'll probably go into them tomorrow, because hour and a half. We're going to call it here for tonight, but tomorrow I'll go into a couple more commands for in regards to spanning tree protocol, layer 2 spanning tree protocol, and then we'll move on to something else. I think I still haven't talked about inner VLAN or DHCP. I think access control list is coming up, so that's going to be let the packets flow. Yeah, for sure. There's a lot of stuff coming up. Today was a big day, though. Spanning tree protocol is a big part of the Cisco exam. Good information to know. I am also super psyched, again, about the books I got today. So Something about the books that I wanted to mention. You all enable Hackermans. What is it? This is different emotes. I'll look into that for sure. I might have to unlock these with better. Oh. Pepe Hackermans. Pepe Hackermans. I'll look into that for sure. Is that like a Steam Labs thing? Like the chat stuff? Or is that something else? But yeah, also about the books, be careful if you are going to look into getting Wendell Odom's guide. You can buy his library, which is everything, for $35, or you can buy each individual volume for $30 and end up spending significantly more. So buy the volume if you're going to get it for $35 and save yourself like $70 buying it the other way. So I don't even know why they have the other way as an option. I feel real bad for anyone who buys volume 1, 2, and then the practice material when you can just buy the library for significantly cheaper and get all that information at once. But really good resource. It's the one that Cisco recommends. I was skeptical about it until I started reading into it today, and I'm actually really excited to jump into this. So I'm going to jump into it after I finish Neil Anderson's source. His course on Udemy. I'm going to jump into the books, and then I'm going to start doing practice tests. And hopefully by then it's just maybe a week and a half or 2 weeks to the test, and I'll be able to talk about this stuff in a way that is equivalent to how it will be practiced and talked about on the exam. So another day down. I appreciate anyone who stops by and takes a gander at what I'm doing here. I will be back tomorrow with some more information. Take it easy, everyone. Thanks again.